Hi everyone. It's really cool to see that the room is full again this week. So welcome, and today we're gonna hear from Sebastian. He's a PhD in Professor Renner's group for quantum information, and he will talk to us. Well, he does quantum foundations, and he also thinks about the weak quantum gravity regime, and he will speak to us about quantum reference frames and observer independent views. And I wish you all very much fun.
Okay, yeah. Thanks for this introduction. Hello everyone, it's nice to see so many of you here. Just get my watch started so we don't take forever. Yes, so I will be talking to you about transformations between quantum reference frames. So this is ongoing research that I do with Esteban Abadina, and I have started working on this for my master thesis last year. Although before that, of course, there's been much other research in the field. So this is one particular approach to quantum reference frames. There are many, and don't move it too much, otherwise the HDMI is again going to yes, I can good. Yeah, so there are many different approaches to quantum reference frames, and the approach you'll see today is one that is particularly motivated by quantum information theory. So let's begin with something that you probably all are familiar with, namely the notion of a reference frame. So reference frames are extremely important in physics because pretty much any observation we do always happens relative to a reference frame. So for instance, if I want to measure the position of a particle, say this atom here, I need some kind of way to assigning positions to that. So I can do this, for instance, with a coordinate system, the blue thing here. Or slightly more abstractly, if I want to measure the voltage of some system in the lab, I also need a reference voltage. So a reference frame can be much more than just a coordinate system. It's a much more general idea. And in fact, pretty much, as I said, anything requires a reference frame. So even if you want to distinguish between 0 and 1, which seems to be something that has kind of an absolute meaning, right? If you want to actually pull this off in practice, you still need to know what 0 means and what 1 means, and somehow the 0 and 1 will be encoded in some physical system. So you still need a reference for that as well. So they are everywhere, and when you use them in practice, then you have to implement them. So reference frames are very physical things. They are required to be implemented in the lab. But in theories, we often abstract them away and describe them, for instance, using the ideal notion of a coordinate system, because we don't always want to explicitly describe the system that the reference frame is built from. Now, there are reasons why we should sometimes care about the physical aspect of a reference frame. So on the one hand, it could be just because we are interested in that, and doing so, we have actually made great progress in the past. So for instance, in GR, it is sometimes very fruitful to actually hold and consider whether a certain phenomenon only really happens because we've chosen some specific coordinate system, or whether we can maybe relate this to some actual observation that you can do in reality with real clocks and real rulers and so on. And I mean, you could even say that when Einstein figured out his theories of relativity, that he had a very physical idea of reference frames in mind. You know, for instance, this his notion of synchronization of clocks was a very hands-on definition using light that is being bounced off of mirrors and so on. Another reason why we might care about describing reference frames as physical objects, besides just general interest, is that sometimes we are forced to do so. There are situations where we are in a specific regime of physics where there are only very few physical systems that can actually do the job of a reference frame. And this has happened, for instance, and this is very important for our cause here, with quantum systems. So sometimes we are just in a regime where there are no classical objects that can serve as reference frames. And so we have to start considering what happens if our reference frame is a quantum object. So this directly leads to the notion of a quantum reference frame. And as you can imagine, it was already maybe complicated to describe a classical reference frame as an actual physical system, but now quantum mechanics has more features or different features than classical theory. And so we might have to rethink how reference frames work if they are made from quantum objects. So reference frames, they essentially give us a way of understanding the information stored in the physical world. And since I've made the point, right, that for everything you kind of need a reference frame. So it is no surprise that people started wondering about whether you could apply information theory, and in particular quantum information theory, to the study of reference frames, and in particular quantum reference frames. And so there is this very mature theory of information theory around the quantum reference frames. Also, another aspect of reference frames that is very well known is that different observers might have different reference frames, right? And so we might be interested in taking the view of one observer and asking, what does another observer see? And so we need a way of transforming between the reference frames. And I mean, classically, for example, you do this in relativity all the time. But now with quantum reference frames, we can ask whether this is also possible. And it turns out yes, and there is also a very extensive body of research about this. And as I said at the beginning, there are many different approaches to tackling the description of transformations between quantum reference frames. So I want to focus on one particular approach, the one I'm working on. And you could loosely title this the QIT, quantum information theory approach to quantum reference frame transformations. So first of all, we care about transformations and we care about quantum reference frame. This is clear from the title because of the reasons that I've just listed. But then we furthermore care about quantum information theory. Why do we do that? Well, because quantum information theory is at the same time very abstract in that it allows us to describe a great many different quantum systems in one go, basically, without being too specific. So that is nice, but it is also quite easy to describe actual procedures that we do in the lab, like preparation of states, transformations you might do on the system, and then finally also measurements. So quantum information theory has it both, and especially the fact that it can describe the things we actually do in the lab very well. This aspect is important, and we call this aspect operationality. So theory is operational if it fits well the actual things that you do in reality. So motivated by this, we want an approach that is based on the quantum information theory of quantum reference frames. Then, of course, we want to transform between reference frames. And there are roughly speaking, two types of reference frames that we're interested in. One is the so-called perfect quantum reference frame. So the picture I have here is more of just a perfect reference frame in general, without necessarily being quantum. So think of, for example, if you want to measure a position along one direction, you might have a reference frame that looks a bit like an axis, or you can sort of compare your particle you're trying to measure its position. You can compare it to this axis, and you can read off the position from there. And perfect just means that this axis is infinitely precise. There are infinitely many subdivisions. Now, going back to this idea of physicality, this is not very realistic. Right? Every engineer will tell you that this is impossible to manufacture. And when you start thinking about quantum reference frames, there might even be fundamental limitations to what this object can be. There are maybe uncertainty relations that limit this. So, although this is a nice idealization, is often considered because it is a nice idealization, we also would like to discuss a bit more realistic quantum reference frames. We call them imperfect, and basically, in contrast to the perfect ones, they are not infinitely precise. And we will see some examples of those later also. So it should be said that before I started working on this, there was already a framework for perfect quantum reference frames and transformations between them that also used the QITM of quantum reference frames. And when I started doing research in this field, one of the first things I worked on was trying to extend this framework to imperfect quantum reference frames. And this is one of the things I'll tell you about. So one central question that now comes up with these with a framework like this is, what does even the point of view of an observer look like if their frame is imperfect? Right? Because everyday experience pretty much tells us that we can measure almost anything as accurately as we want. So our intuition is more towards perfect reference frames. And then, okay, well, quantum reference frames is still kind of a stretch, but certainly imperfect quantum reference frames is kind of hard to imagine. So one question we can ask is, what is the view of an observer with an imperfect quantum reference frame? I will come back to this question right at the end. All right. So this was a long introduction, but I think it's important to stress these points, why we care about reference frames, why about quantum reference frames, why quantum information theory, why perfect, why imperfect, and so on. But now we can get started. So let me begin with, again, something that you were probably familiar with from your quantum mechanics courses. Although you might not have seen this in this language that I will use, but so it will probably just be kind of a translation of what you already know. So let's see, let's consider two observers, Alice and Bob, and they will accompany us for the rest of the talk. And let's also assume that in order to get from Alice to Bob, Alice would have to move by an amount delta x, some number. Now Alice can observe, let's say, some quantum system S, and she might see the state psi, and the subscript S bar A is here to indicate that this is the system S viewed from A. Okay. Because it is now well known that, oh yeah, I should maybe move my cursor out of the way. It is now well known that Bob can also observe this the same system, but in order to get the state that Bob has, we have to translate the state. And this happens with this unitary operator, this translation operator. P is the momentum of the system, and delta x you have to sort of feed into this transformation as a parameter. Okay. Now let's reformulate this a bit more in the language of reference frames. So the bar A and the bar B is already kind of hinting at that there is actually a reference frame in play. Because let's say Alice is, I don't know, measuring the position of this system. To her, it naively looks like she can measure the absolute position of this thing. But of course, in reality, what she is doing, she is actually using her reference frame, which we call A. She's using her reference frame to measure that position. So really, if we're looking at Alice from the outside, we will see that she's actually measuring the relative distance between S and A. And so this is a central theme of reference frames. Sort of the physical quantities that we can measure are relative quantities. But when we use a reference frame, to the untrained eye, it looks like we're measuring absolute quantities, just because we are making use of the frame. Same goes for Bob and his state. And I'll go one step further. This delta x can actually be seen as a property of Bob's frame. So Bob will have a frame called B, some physical object. And there's this observable xb from A, which is essentially the position of Bob's frame seen from Alice. And in this case, this observable has a definite value, it is delta x. And so Alice knows that if she wants to transform her state to Bob, she has to do the transformation by that amount. Yes. Now, translations are not the end of the story, of course. Maybe Bob and Alice are related by a rotation, or there's some other abstract transformation that might happen between them, like, I don't know, using a different voltage in the lab, like the example we had before, or using a different phase for a laser, something like this. In general, the circumstances will tell us what kind of transformations we're really interested in. And these transformations are then those that we need reference frames for. And so in general, we'll have some group G that tells us about what the reference frame needs to be doing. So we then say that the reference frames are reference frames for G, in the sense that transformations of G can be measured relative to the frame. Okay, so for the case of translation, we just had the example. In the case of rotations, it might be that your frame is some kind of pointer in space, and now you want to sort of see how something is oriented relative to the frames of this thing, and I just compare it to the frame, and I can find the relative angle. And now the group of transformations is the rotation group. Okay, so what changes if I replace translations with a general G? Well, first of all, this delta x becomes a G. It's now the transformation that one has to do to get from Alice's situation to Bob's situation. This thing that transforms the state becomes a unitary representation of my group. This is also something I have to sort of choose according to what I'm interested in. The circumstances will tell me which representation I have to use. And then the G is now the value of what we call the orientation observable. So before it was the position observable, but now more generally called the orientation observable. So this is how Bob's frame looks like from Alice's perspective. And this is what Alice can read off the transformation she has to do in order to get to Bob. All right. Maybe this is a bit too early. So one thing to notice is that in all this, we could call this a little framework of reference frame transformations. All the frames are classical because they always have this definite value for the orientation. All we ever care about in a frame, really, to do the transformation, is the orientation, right? So it is without loss of generality that we can reduce the reference frame to just that aspect. And so in particular, we can just label the states of the reference frame by the possible values of the orientation. And so this leads us then to the definition of a classical reference frame for G. It's essentially a classical system where the states are labeled by the possible orientations. Okay, so here's the example I've kind of sketched already with my hands. So this is the group of rotations around one axis, and the reference frame might be a pointer that just gives me one direction in space. And if I want to, the way I use this frame is by comparing the object I want to measure its orientation of relative to the frame, and then I can measure this sort of relative angle between the object and the frame. Okay. So much for classical reference frame transformations. Let's now go to quantum reference frames, and let's begin with the perfect one because they're slightly easier to deal with. So the idea behind the perfect quantum reference frame is actually quite simple. It's essentially a classical reference frame, plus we allow all the quantum stuff. So our frame that we had before, the pointer can now be in a superposition of two states or more. Now no longer that clear how you would measure a relative angle. I mean, now the outcome is no longer certain, as is often the case in quantum theory, so this is not really surprising. Also, of course, having superpositions allows the frame to be, say, entangled with a bunch of other systems and have all kinds of quantum features that we know and love. So the definition is then also quite straightforward because we already know the definition of classical frames. It's, well, okay, it has to be a quantum system, so we take some Hilbert space HR, and it still has to, at the heart, contain kind of this classical frame. So we require that there are these states called classical frame states. They're labeled by the group elements, and they essentially other states that are inherited from, yes, I said, from the classical frame. What makes this frame perfect is that these classical frame states are perfectly distinguishable, and we achieve this with this orthogonality relation. So if the two states are perfectly distinguishable if they are orthogonal, and so we want them to be orthogonal if the G is not the same. Now, for those of you wondering about this delta function, this is a delta function on the group manifold. It is infinite at the identity and otherwise zero, and in a way that plays nicely with integration on the group. So it's essentially a generalization of the delta function, you know. But okay, we will never need this fact again. It's just kind of because I know someone's very interested in this. Now, as I've also said before, perfect quantum reference frames, or in general, perfect frames, even classical frames, are not very realistic. Now, let me give you a few explicit examples why for quantum reference frames this is particularly so. Okay. I think I'm slightly quicker than I'm used to, so that's good. I can slow down a bit. Okay, so first example, let's take a quantum particle. Let's take the group of translations along one line, and we know that the position eigenstates of this particle are mutually orthogonal, and there is one for each position, one for each translation. So that actually makes a perfect quantum reference frame for this group of translations. However, the position eigenstates are not really physical. They have infinite energy, so cannot actually even approximate them. At some point, we will spend so much energy by doing that it would be impossible. All right. Let's be even more ambitious, take the same particle, but now not just the translation group, but also the group of boosts. Together they form the Galilei group. The classic, I mean, this is a classical group in the sense that the boosts are classical, so non-relativistic. But still, now what you essentially need is a set of states that have a definite value of position and velocity at the same time in order to really build this perfect frame, which doesn't work because the quantum particle has uncertainty relations to fulfill. So you cannot even, not even in principle, you cannot actually build this frame. There is a trick. You can make the mass of the particle infinite because then the commutator becomes zero. But again, it's not a practical trick. This is an interesting example. So take the group of rotations in space. Okay, we're doing quantum theory, so let's take SU2 or not SO2. You can use, let's say, spin 1/2 particle to indicate the direction in space. But this is only really a good indication of direction if you already know that the direction is either in this direction or that, and everything in between is it's very bad at that. And it turns out the representation theory of SU2 tells us that if you really want to build a perfect quantum reference frame for rotations out of a quantum system, that this quantum system would have to have an infinitely large spin. So yeah, it's also, again, not really practical. There are many more, but let's move on. So I guess the conclusion is here that perfect quantum reference frames are really an idealization, but they are often useful. So they're often studied, and we'll also take a look at them now and first discuss this framework for perfect frames before we then go to imperfect ones. So we get to later. All right. So for the perfect version of the framework, let's begin in the points of view of our two observers, Alice and Bob. This is, by the way, also kind of novel relative to previous research. The previous paper on this framework started from a different approach from some people call an external reference frame that was then used to set everything up. Here we already start with the user observers. We do kind of the opposite. So again, there are these two observers, Alice and Bob. They should each have a perfect quantum reference frame, and there should also be a system S that they're just observing. Right? So as I said, Alice and Bob have perfect reference frames, HA and HB, and they're both isomorphic to this perfect reference frame state perfect quantum reference frame Hilbert space, and then the system just has some Hilbert space HS. Okay. Now, essentially, Alice has a perfect quantum reference frame, which is really a classical reference frame in disguise with additional features. Right? So she should be able to do everything that she could do if she had a classical reference frame. And now remember this feature of reference frames that they turn relative quantities into absolute quantities. If you forget about the fact that you're using a frame. So motivated by this, we now assume that using her perfect quantum reference frame, she can see the two Hilbert spaces of the other two systems, so Bob and S, perfectly. So we give her full access. We mean with this that she can have any state that quantum mechanics sort of allows on these two Hilbert spaces. You can have any observables, you can do anything, okay? Because she has a frame that allows her to do so. Basically, she has a lab frame for these two systems. But her own reference frame still survives. It's still some kind of a quantum system that's still there. Although she cannot really use it to observe itself. It's kind of a problem. So we don't yet, I mean, a priori, we don't really know what we should do with this. The solution will be that we give her access to this, but then have some restriction on the kind of states that she can have there. The same goes for Bob. Of course, now the restriction is on his part. Right. Let's now talk about this restriction. And this is where QIT comes in. So let me introduce a concept called the cheat world. So it looks more complicated than it is. So basically what it is, it takes a state, sigma, and then applies every possible transformation according to the group and produces a mixture with equal probability. So what does that mean? In quantum information theory, a mixed state of this type is describing a situation where we don't really know which of the states is really there, but we have some probability assigned to each possibility. In this case, the probability is uniform, right? Every possible G could have acted on this state. And so really this describes, after we have applied the cheat world, this describes a state of affair where we have no idea whether any transformation has been applied at all, and if so, which one. So this leads then to the interpretation of this cheat world, namely by observing that, I mean, the reference, if we had a reference frame, its job is to tell us about transformations that G is doing in the system. The reference frame allows us to resolve these transformations. Think about, again, translations, for instance. If you have a reference frame for translations, then you can track whether things are being translated or not. If you don't, then you have no idea. So this kind of produces this state of no idea, right? And so we say that applying the cheat world for state is equivalent to just forgetting that you have a reference frame, or throwing it away, or somehow losing it. And this is actually the basis of the quantum information theory of quantum reference frames. So similarly, if you have a state which is already invariant under this cheat world, then you're already kind of in this state of not having a frame. And so we say, then there is no frame. So these are kind of the two pillars of quantum information theory on which the framework is then built. And it can help us to answer this question about Alice's own frame in her point of view. Right? We've said that she cannot use her own frame to observe itself. So she essentially doesn't have a frame to observe her frame. So there's the absence of a frame. So what we really need is that the part of her state that describes her own reference frame must be invariant under this cheat world. Okay, so this was just kind of to show you the beauty of quantum information theory and how it kind of comes in nicely in this framework. Let's now go to the transformations. So we again have the setup from before. Alice will observe some state. Now it's not just of S, but also of her own frame A and of the frame B of Bob. And then Bob will observe also another state. and there is going to be some unitary, this U dagger A to B. One second. And we call this the quantum reference frame transformation. Yes, there's a question.
I was just curious if the sigma notation still means like a normal density operator, or
Yes.
is it something special?
Yes, I should have said this. The sigma is a density operator. Yeah. Yes.
Why is the transformation between reference frames always a unitary operator?
That's a good question. So the short answer is we assume that it is. And I guess the slightly longer answer includes a motivation for why we assume that it is. No, I mean, this is an assumption we make. So I would say it's fairly reasonable to assume that it's unitary because the frames are perfect. So there's intuitively in a way there's no information that can be lost when you go to another frame because all observers are able to see everything and anything. When we then go to imperfect quantum reference frames, if you were to build this framework for imperfect quantum reference frames, and we'll see later actually that it's not so easy to do that, because there we first of all have no idea what the view actually looks like. That's why we asked the question in the beginning. And there it's very well possible that the transformation is not unitary because of the frames being imperfect. Yeah, that's the reason. Okay, so notice that the reference frame transformation does not contain a parameter G or delta X that we have to input, because the orientation is already stored in the B part of Alice's state. So the job that this transformation now has to do, it has to go look at this state and then do the corresponding transformations. Of course, it should reduce to the classical case if B's frame is actually in a definite state of definite orientation. So if B is in, say, ket G, then the G transformation has to be applied to the system. And so yes, this is basically what I said. So we require this compatibility with the classical case. The transformation has to look at which state there is and then apply the correct one to do the transformation. We call this the control requirement, and I'll come back to why that is called this way. And so this idea has also been around for a while. We're not the only framework that uses it, of course. So let me illustrate it with translations again. So on the left, we're in Alice's view, and this is marked by the fact that Alice is connected to the axis, sort of. Let's assume that Bob is in a position eigenstate, so it's actually in a ket G state. And for simplicity, let's also assume that the system is in a position eigenstate. We now require that the relative distance between Bob and the system remains correct when we do, remains the same when we do the transformation. And this ensures that we are compatible with the classical case. Now, the reason this is called control requirement is because this now generalizes bilinearity to more general states on Bob's frame. And so what you end up with at the end is a so-called controlled unitary. This is a concept from quantum information theory where a transformation applies different unitaries on some subsystem based on the state of another subsystem. So the second subsystem controls which unitaries are acting on the first one. Then there are some other assumptions that we have to make, like that mostly assumptions that are sort of implicit in the classical case, like we want some version of the principle of relativity to hold. Transformation back from Bob to Alice should be exactly the same as from Alice to Bob, except that the roles of A and B are exchanged, and so on. Okay. With these assumptions made, motivated, we get close to actually getting a unique form of this U. And for instance, we find that Alice actually gets shifted to the correct position where she should be. But it's still not quite unique. And the freedom of choice we still have with these transformations has exactly got to do with this, with the reference frame of Alice seen by herself. So this kind of mystery that we still have there. So to make progress in this direction, we came up with this idea of observing independent view, and you can see what that means. But let me first use kind of another idea from quantum information theory, namely that you should be able to extend your system at will by adding new systems, adding new stuff, and the framework should still work, or you should be able to remove stuff again, it should still work, and so on. So in quantum information theory, we often want this sort of composability. We also want it here, so nothing stops us from taking a third observer, Charlie, and forgetting him immediately. So we go to Charlie view, and there the Charlie will see A, B, and S, but now we want to get rid of Charlie, and so we know how to do that now because we remember the blue box with earlier with the QIT interpretation. Basically, it involves the G twirl, but we also want to remove every trace of Charlie, so we also trace the Charlie subsystem out. This is kind of a standard technique in quantum information theory to remove a subsystem. So we do a combination of both. What do we end up with? Well, the state we now get is, intuitively speaking, a state that still contains information about A, B, and S, because we have not killed anything like that, right? But it's not a state understood relative to any observer. So we call this an observer-independent state, and this is now where the observer-independent view comes from. So because A, B, and S are still in there, and all the relative degrees of freedom between them are still in there, there should be a way of getting back to Alice and Bob's view. So we assume that this is the case. So there must be maps that go down from there. And of course, between Alice and Bob, we have the reference frame transformation. And so assuming that this kind of stuff can happen, actually constrains this quantum reference frame transformation uniquely. And yeah, this is one of the nicest results that we have had in this approach. It is, I should say that this gives exactly the transformation that was already considered in previous research, but we arrived at it from a completely different angle. So they came from this kind of top-down view where you had some external frame that acted like a lab frame, and then you build stuff from there, whereas we started from the point of view of observers, and we end up with the same framework. Okay, now I actually have to speed up a bit. But this is basically it for perfect quantum reference frames. I mean, there's a lot more to be done here. Like you can now do examples, and you can study the structure of states and all kinds of things. And there are still many open questions. Like we don't really know what Alice's reference frame from her point of view really means physically. This is still an open question, even for the perfect case, actually. So let's go to the imperfect case, since that is a bit more realistic, and we also want to explore this. Basically, an imperfect quantum reference frame is pretty much like a perfect one, but the different states, the different classical states, can no longer be distinguished perfectly. So now the classical states are no longer ket G's, but ket gamma G's, just to distinguish them from the ket G's. And that they're no longer perfectly distinguishable just means that their overlap is no longer a bunch of delta functions. Sorry. So the example that I always have in mind when I think of an imperfect quantum reference frame is take again a quantum particle, the Galilei group in one dimension. So remember, this is translations and boosts along an axis. And we have seen before that you cannot localize these states perfectly because of uncertainty relations. But you can try your best, and then you get something called coherent states, which are basically as compact as it goes, and they're sort of symmetric in phase space. Their uncertainty and x and p are sort of equal. And well, in position space here, they look like Gaussians, and of course Gaussians have overlap, right? So although they're centered over two different positions and so correspond to essentially two different group elements, they still have overlap and are perfect because of this. Okay. Let's try to repeat the thing that we did earlier for perfect frames. I mean, I gave it already away, it's not going to work, but let's give imperfect frames to Alice and Bob. And one thing we can now ask is, we can try to do exactly the same thing we've done. So what would be the view of Alice and Bob if they're imperfect frames? Of course, this being the sort of the final big question I want to answer today, we cannot answer it right now. So we don't really know. A priori, at least, we don't know. So we need to have some kind of other idea of how to get there. And so there are actually two ideas that would then work together. So instead of starting in, let's say, Alice's view, you can just, again, invent Charlie, say that he has a perfect frame, and then there we know how to set things up, and then go to Alice via some transformation. And on the way, you can also forget Charlie again, right? So really the underlying assumption here is that our framework should be compatible between perfect and imperfect frames. So there should, I mean, it kind of makes sense. You might have one system that is actually a perfect frame, the other one might not be, right? So, so this certainly kind of makes sense to assume. Of course, we have just offloaded the problem somewhere else. Like, we don't know how to transform to an imperfect frame. We just know how to transform between perfect frames at this point. But this will be easy to solve, actually. The second idea is that, again, borrowing this idea from quantum information theory, that you should be able to extend your system at will and that nothing can stop you from doing that. We should also consider that quantum reference frames should just be able to be improved by adding new stuff to it, and maybe be replaced by better frames and so on. So we can improve a quantum reference frame until it becomes perfect. I guess ideally we'll never get there because it's sort of impossible, but still we can sort of think that this is in principle possible. So essentially we can think of an imperfect quantum reference frame as some sort of subset, actually subspace, a perfect quantum reference frame. And the best way to treat this mathematically is to come up with an embedding of a imperfect quantum reference frame into a perfect one. So what is that? Let's talk about the embedding first, because this then can help us with the first idea. So the embedding, I call it E, is basically a linear map from the Hilbert space of the imperfect frame to the Hilbert space of the perfect frame. It should have some nice properties, like it should be an isometry, it should keep the inner product the way it is. It should be compatible with the representation structure on both of these spaces and so on, but we don't really need to go that much into detail. Turns out that with a few very well-founded assumptions, this is again unique to given. Okay, so this embedding is also quite easy to interpret what it does. But just imagine that on the right there's some state that you want to embed. What the embedding does, it goes through all the group elements and it checks whether the state you have sort of matches each of these classical frame states. And if it does, it produces a ket G as an output. And of course, because these imperfect ket gamma G's have overlaps, generally, and I mean, I guess always, you will get some kind of widespread in the perfect frame. For instance, take again our favorite Galilei group with the coherent states. So this is a coherent state centered around some point A. VA is a translation parameter, and B is the boost parameter in the group. And so what happens, because these classical frame states of the imperfect frame have overlap, you end up with sort of this kind of spread Gaussian shape in the perfect frame. If the imperfect frame had been perfect already, then this Gaussian would just be one peak at the middle position, one delta peak actually. So now the imperfection of the frame kind of shows us this spread. All right. So now to the other idea, the first one. Let's begin with Charlie's point of view again. Let's assume that he has a perfect frame. We can set things up there. And then let's go to Alice's frame and for now assume that her frame is also perfect. Then already working towards the conclusion that really her frame is imperfect, but it can be seen as part of this perfect frame. So assume that Alice has a perfect frame for now. There are essentially two ways of how to get to Alice. We could just do the reference frame transformation from Charlie to Alice, but then we still have Charlie and we don't really want him because we don't really need him for the point of view. So let's go the route of forgetting. So we forget Charlie, go up into this observer independent view, and then down into Alice's view. So that's what this arrow means. So you end up with the state in Alice's perfect frame. And now what do you do? Well, if you're lucky, this state is actually in the image of the embedding, right? And it's already an imperfect state. But we can show that this is quite typically actually not the case. So when you do this kind of stuff, you will pretty much always end up with a state that is not a truly imperfect state. And so you have to find some way of getting to the nearest imperfect state to really answer the question about what Alice sees. Now, luckily, the embedding helps us again, because the adjoint of the embedding, so the dagger, turns out to be an orthogonal projector onto the image of the embedding. So this basically just gets us to the closest point in the embedding image already. So what we can do is we apply this, and now we truly get to the point of view of Alice in her imperfect, using her imperfect frame. And let's look at an example now of what this means. So now this is the answer to the question. And we're almost done, actually. Too much on time, I think. Let's begin with some state in Charlie's U. So I will prepare Alice's frame in some state phi. And then there's some other state on the rest, this blue thing. And also, of course, Charlie will have some state on his own part of the, on his own reference frame, but because we basically forget him immediately, we might as well just leave that out. So then we do this whole chain of things, and what you get is this, and I will explain what it means, but you might already notice that I sort of left out Alice's part. And so I could have kept it in, but then the expression is just more complicated. And because we don't really understand yet what that part means, we just focus on the things that we know. And so I just remove again Alice's part. Yes?
This is now a state for Alice in her imperfect frame.
Yes. Yes, so this is the state that Alice attributes to Bob's imperfect frame, the system, but seen from her imperfect frame, yes. So this is the answer to the question, essentially. This is what she sees. Let's analyze this. So this U dagger BS is essentially a sandwiching of this blue state with the unitary that does the transformation corresponding to G. So again, you see that this is a mixture. The thing goes over all G's in the group and applies all the G's, but this time it weighs them with this prefactor there, with this overlap squared. So this kind of selects which G's have to be applied. And now let's take again the Galilei group. Let me prepare this red phi state in a superposition of two classical frame states. I have here plotted this overlap because this is the essential thing that governs the result. And as you can see, there are two peaks. I mean, the fact that there are two is kind of expected from the fact that we had at the beginning this superposition of two states. But then each peak is kind of broadened, and this is for the same reason as in the previous graph. It's because the frame is imperfect. Of course, if the peaks are closed, then they are no longer distinguishable, and you start to see this kind of idea that an imperfect frame cannot perfectly distinguish things. So now the fact that this is a mixed state, like a probabilistic superposition, a probabilistic mixture of different states, again corresponds to the situation that we don't really know, or in this case, Alice doesn't really know which state she really has. Okay, so this is the manifestation of her imperfection, or of the imperfection of her frame. She cannot really resolve the state because her frame is not perfect. Okay, so
Small
yes,
technicality, but there should be a U after the sigma as well, right?
okay, good
Yeah,
point.
just
So actually no, but
Okay.
okay, I can explain why. So yes, so the Yeah, I should have said this. So what I mean with this U is a super operator. So I mean the sandwiching already. But of course, if I put the sandwiching, it goes off the side. So this yes, yes.
If Alice still had her imperfect frame, but Bob had a perfect frame or better one, perfect frame, would the graph kind of change, or would Alice still not be able to kind of prevent the states or like prevent the smearing out?
I mean, in this case, since we're jumping into Alice's frame, which is still assumed perfect, it would still look like this. But if you then go to so okay, now it becomes difficult because you then go to Bob, you have already lost the information because you were in Alice's point of view. So you will sort of inherit that, although you will not lose more information by going to Bob because his frame is perfect. But if you go to Bob directly from Charlie, then you should not have this kind of problem. Yeah. Then you will have sharp peaks. Yeah, so this kind of answers the question. And so I guess the short intuitive answer is that the point of view of Alice with an imperfect frame is kind of fuzzy in this sense that it corresponds to a probabilistic mixture. Sorry, a probabilistic mixture of different states. All right. So what have we seen today? Well, we have seen an observer first approach to a framework of quantum reference frame transformations. So observer first means that we started the point of view of observers. They were inspired by quantum information theory. Then this framework, we showed that it was that it worked well for perfect quantum reference frames, and then we extended it to imperfect ones through this notion of the embedding. And of course, also the story is not over for the imperfect ones. There are many things you can do now. I haven't actually talked, for instance, about what the transformation between imperfect frames would look like, but it's roughly along the lines of embed first, do a perfect transformation, and then do this e-dagger at the end. But yeah, we don't have time for everything. So just because that was in the title like this. So we did this embedding of imperfect frames, and this is how that was made compatible. Yes.
Just a quick question, because there's the quantum information theory approach to quantum reference frames. So I'm guessing there are other approaches.
Yes.
And would like are they equivalent to what you guys found here, or do they look completely different, or do you get similar results? Or
so the other approaches to quantum reference frames and their transformations, they are in some respects similar. Certain parts are equivalent. So for instance, one way to see it, although this doesn't paint the full picture, but our framework can sort of be restricted to become different other approaches. But then in another sense, we could also extend our approach to again become equivalent to those approaches. And I guess overall, this is also an open area of research. So there are these different approaches. They are based on different assumptions, which means that they are applicable to different circumstances, which makes each of them very interesting. And of course, very interesting is also the question of how do they fit together. And this is still pretty much ongoing. So I cannot say that this is this is equivalent to anything else, because it most certainly isn't. Or at least we don't understand if it were. Yes. Yeah.
Could you maybe like give an example of an instance of people doing so? Like, because I have like a hard time imagining right now how thinking about quantum reference frames without quantum information theory would be possible, because that's like
Yes.
Like the problem that we're trying to solve. So,
yes. So a very famous different approach to quantum reference frames is the so-called perspective neutral approach. And so the main mathematical difference is that you don't want gene variance for your states, but some kind of coherent version of gene variance. So you can also kind of just draw it here quickly. So you can require something like this, or now this is kind of a pure state version and a coherent version. And this can be, I mean, this is the sense in which what I meant with if our framework is constrained, then you can actually constrain it to states like this, and then you kind of get something like perspective neutral. But then, of course, you could also try to maybe purify our framework by going to a pure version of gene variance, and then you can again end up with this. So the reason they care about a coherent approach to gene variance, with invariance under the group function, I think originally goes back to quantum gravity, where this kind of certain approaches of quantum gravity sort of suggest something in this direction. There's also the Page-Ruther's formalism of time evolution in quantum mechanics that sort of looks a bit like this. There, the group would be the group of time evolution, just time translations. So yes. Also, I guess one big downside of the quantum information theoretical approach is that while it works very well in a lab, right, because it's operational, you can apply it almost immediately. Well, I'm a bit exaggerating. It's probably a lot of work. It is operational. It works well in labs. If you want to also include the whole lab equipment in your description, this kind of becomes difficult because it's kind of based on the idea that you have a Heisenberg cut and all that. So, okay, I think let me continue then. Yeah. And there are some other approaches that I don't know much about, unfortunately. Yeah. So, yes, and then finally we answer the question of what the world looks like to Alice through the lens of her imperfect reference frame, and it looks fuzzy. So now, what can we do with this? Well, first of all, there are open questions. For instance, we have now sort of assumed that we can always make this frame bigger, and so this was the motivation for the embedding. But what if you only have a limited amount of resources? What if you cannot justify that this thing can be made bigger in principle? Or even, what if you cannot just invent the Charlie and then get rid of him again, and so on? Is there, for instance, some kind of consensus that maybe n observers could have about the perfect versions of their states? Because now each observer sort of has a different imperfect view on the world, and some observer might have access to some information that some others don't. And in fact, we can show that this actually happens. So now it would be an interesting thing to see whether somehow they can come together and convene and sort of build the bigger picture from it, or maybe they can't. But this is something that we're working on, or at least want to work on. Then there's still this mystery about what physically is in Alice's own frame when she looks at it. This is not something that typically happens in classical frames, so we don't really have an intuition for this. And then, of course, there's a bunch of applications that we might be able to do. So it has already been applied to single particles and questions about those. But maybe we can apply it to some paradoxes and quantum reference frames, because there are some. We've not talked about them today, but there are. Maybe quantum gravity, why not? There are notions of ideas of fuzzy space-times, sort of indeterminate, yeah, so maybe this can help. But yeah, the field is pretty much active at the moment. There's much research being done. There is much research to be done. So it's a very exciting time. And I hope I could excite you as well. Thanks for coming, and we still have time for questions, I think, although now we're kind of at the mile. Yes. Yeah, okay, I can answer your question.
But ask or
Yeah, I guess.
So,
Yeah,
so the last question maybe is, so when if I understand it well, we have like the system A, system B, and then system S, and how they view system S we're trying to describe. And now we have this imperfection, which tells us that A and B in itself may be also like, let's say quantum and also like in a way fuzzy. But still, even in these imperfect frames, A and B are not measuring S. right? So, so
Yeah.
it's actually maybe it boils down to the question that he was asking, that this U was always unitary, but it may also be a projection, right? In a sense, no? If A and B start to measure S in some definite way, or are we assuming that that's impossible?
Yes. So at the moment, we haven't actually, in the framework, we haven't really talked about measurement.
Okay.
So we're just thinking of the states. Now, of course, when a measurement happens, yes, you have some completely positive trace preserving map that actually does the measurement. And well, it kind of depends on what the outcome is and so on, whether the information actually increases or decreases about the system. So at the moment, we don't do measurements, and I guess this is why it's unitary. And really, the unitary we had here, this was inherited from compatibility with the perfect case. So this was not, we didn't assume that the transformation has to be unitary for going from Charlie to Alice's imperfect U. In fact, it is not. But just that, I guess this part in it is, but then it's a mixture of those and so on. Yes.
So quick follow-up. So that means that we are assuming that Alice and Bob have more or less the same information about the system S.
I guess this is only true if they have the same kind of bad frame. Maybe Alice has a much better frame than Bob, and she might have more information about S. And I mean, I haven't really touched on this, but it is possible to have different frames for Alice and Bob. They don't all have to have the same kind of one particle of coherent states. Maybe one can have a different one. It depends on this, I would say. Yes.
What happens if we do kind of like these Wigner friend experiments happening? Would it make kind of a difference? Because in the first talk with Rainer, we saw that there's kind of this inconsistency, like between when these different observers kind of concatenate like logically statements, and here we can transform between the reference frame. There are also some sort of.
So I don't know how this framework can be applied to Wigner's friend, because okay, although we say that Alice sees Bob and Bob has a Hilbert space B is only the Hilbert space of Bob's reference frame, and not of Bob and his whole lab, not of his measurement device. So we are not really in a situation to discuss Wigner's friend at this point, although maybe we could by extending our methods a bit, but I think it would be a lot of work. I cannot give you a good answer right now about this. I want to say something else. I don't remember, sorry. Yeah. Yes.
I'm not sure if I understood the answer before properly, but tying into it, do we have any notion how imperfection carries over, like from different observer standpoint, especially, for example, in the sense of self-referential systems? So if Alice tries to make a statement about what she would see, what Bob would see, what she would see,
Yes, yeah.
Does that result in some sort of like increase in fuzziness, or what happens there?
So the kind of situation you're describing, what Alice thinks Bob sees, basically, that is something we can answer with this framework, and it's basically the reference frame transformation from Alice to Bob when both of them are imperfect. So again, the idea is that you'll have some state that Alice has, so she thinks she has it, at least. I mean, she's not sure, right? So you take this state, you embed it again, you do the transformation perfectly, you do the E dagger, and this will be your best guess, or Alice's best guess, what Bob's state could be. And I mean, one thing I've now not mentioned at all, but I mean, I guess now I can. It's there's really this transformation with the E dagger is very nice, because it's intuitively the first thing you would write down as a first guess. You can basically take the perfect form of the reference frame transformation. You can write it out in terms of integrals over sorts of ket bars of G and G dashes and so on. So there are these perfect ket G's in there. And if you now just naively replace every ket G with a ket gamma G, you do the right thing. This is basically what you get. So it's also quite nice that you get the first intuitive idea. Oh, yes.
Yeah. the fact that in this framework we are still not thinking about the measurements, this implies also that we are not still either thinking about Heisenberg cuts or things like
Yes.
that.
So,
I mean,
yeah,
yeah, I don't know, when like we are describing the the imperfect reference frame of Alice, we are still seeing it from our perspective, our like Heisenberg cut perspective. I mean,
so I would say in this framework, we do think a bit about the Heisenberg cut, and in the sense that each observer has their own Heisenberg cut, so they will see, they will, let's say, let's take Alice, okay? Not a cut. Heisenberg cut. So the difference between what is quantum and what is classical in there is the boundary. So Alice will see will see her own system A and then B and S, and this is quantum. But then all the devices in her lab that she might use to do a measurement eventually, this is not part of the quantum world. This is behind the cut. And then Bob has a similar cut. But of course, these cuts are all kind of essentially compatible, because the devices of Alice are also not part of Bob's quantum description. So they all kind of agree in this sense, but still each observer can have their own cut essentially, because they all have their own labs in this sense. So we do think a bit about it, although we never actually do a measurement then.
okay, just the reasoning of like, I mean, Alice couldn't really do the Charlie, like all the operation passing from Charlie, and
Yeah.
How can she like?
Yeah, I mean, okay, yeah. I think I know now what you mean with the.
It's only our
yes.
perspective of
Yeah.
theirs.
Yes. Yeah, we as the architects of this
Yeah.
framework, we look at it from the outside. Yeah, no, I mean, this is valid. I think this is true.
One more question, actually, would it be possible to upload this master thesis to the WhatsApp group or share it somehow that we all have access to it, or would that be possible?
Yeah, so it's actually published on the ETH research collection,
Okay.
Yeah, maybe we can leave it on the web page or something.
although it has a lot of typos in it. I recently read it a lot because we are writing a paper at the moment. This has not come out yet, unfortunately.
Okay.
It will be a few more months probably, but this is basically about all of this and more. So yeah, it is in the works, but it's not finished yet. But the thesis is there. Yeah.
Right, so we'll try to link it and send the info to the chat.
Actually, if you find my personal webpage, I have there also an errata file for the.
All right, so we'll upload both.
So you can actually I mean, my website then links to the research collection, but the file is also there. There's some problems with daggers and so on sometimes, but I mean, it happens. It's a minor things. You had a question, right?
Yes, so it goes back to this question. What we essentially do is, when we imagine Charlie, is that we do a thought experiment. Okay, this Charlie should in principle be possible with like infinite mass and so on. And then we engineer with this thought experiment, this is what the transformation should look like from Alice's imperfect frame into Bob's imperfect frame. And then we can apply this operationally without going through Charlie, which we cannot do operationally. Yeah,
no, it's true. At some point, you need this Charlie as a perfect reference frame, because so if you want it, so in this sense, if you're very strict about only doing the things that you can actually do, yes, then you probably shouldn't do it. But I mean, so we're now stretching the boundaries of operationality quite far. Yeah. So I mean, yes, I agree. It is an observer first approach, but still it requires some assumptions. I mean, this is also why there are these open questions at the end, right? We really know what happens if we cannot assume these kinds of things.
All right, I think we like if anybody has last question, or I think we've had some already. Let's thank Sebastian again for his very interesting talk.